And I'm Alexander, with Rachel filming.
Hello!
And this is our Atwood lab. The Atwood machine is a device consisting of two blocks and a light pulley that demonstrate the consistency of Newton's laws. The Reverend George Atwood was a tutor at Trinity College, Cambridge, when he published a collection of experiments in 1784. It explained and shows the theory and design of the Atwood machine. The most relevant formula we use for this lab is m2 minus n1 times g equals m1 plus m2 times a, when m2 is the larger the masses, m1 is the smaller, while g is the force of gravity and a is acceleration.
The problem we were asked to solve in this lab is whether it is possible to predict the acceleration of an object using the Atwood machine formula. Our hypothesis was that if the theoretical yield and the actual yield of two formulas is similar, then it is possible to predict the acceleration using Atwood's formula.
First, we have to calculate the theoretical acceleration using a formula derived from Atwood's original formula. We write down our givens. Mass 1, the lighter mass, is equal to 50 grams. Mass 2, the heavier mass, is equal to 100 grams. And gravity, our constant, is equal to 9.8 meters per second squared. And our unknown is acceleration. We write down the theoretical formula. m2 minus m1 times gravity is equal to m1 plus m2 times acceleration. We arrange the formula so it'll equal to acceleration. We substitute the values. We cancel out the units, and acceleration is equal to 3.3 meters per second squared.
Here we have the Atwood device, which consists of a clamp, light pulley, and two masses, a lighter one and a heavier one, which represents mass 1 and mass 2 in our formula. To do the experiment, we're going to raise mass 2 over mass 1, let it go, and time how long it takes to hit the ground in order to find our acceleration.
Now here is our actual experimentation. When I let go of the string, Rachel's going to time how long it takes mass 2 to hit the ground, which will help us calculate our acceleration. So on the count of 3.
Okay.
1, 2, 3.
Our time is 0.8 seconds.
It's important to do more than one trial so that your results have credibility and repeatability. And so this is our second trial. So on the count of 3 again. 1, 2, 3.
Our time is 0.82 seconds.
This is our last trial. 1, 2, 3.
The time is 0.78 seconds.
After doing our trials, we found that the displacement equation was the best to find acceleration. Doing all 3 trials and taking the average of the time, we found that it is 0.8 seconds. Our distance from the top of the table to the floor was 0.99 meters, and our original velocity and original distance are 0. So now all we need to find is our acceleration. By plugging in all the numbers, we soon find that acceleration is 3.09. And our percent error, which is actual minus theoretical over theoretical, taking our answer from the theoretical equation, which is 3.30, we find soon that our percent error is less than 1%, which is astronomically awesome.
Our data in this lab proved that our hypothesis was correct because the actual and theoretical yields were so close together, less than 1% error. However, as close as our data was, there was still room subject for human error. And in other labs, the human error could have been much greater, and thus the percent error would have been much greater. So finally, the Atwood machine as a predictor for acceleration using gravity and other sources is accurate, but it is much dependent on human error as any other thing is.